Okay, before we jump on to the complexity thing, let's just take a moment and quickly look through. Oh, you can't see this. There, that'll help. Make sure this is recording good. Yeah. No, maybe. Yeah, there we go. Let's take a moment and look at the course classes unit tests, because the unit tests are going to be far more complex than what we've seen so far. Not too bad, but they are going to be more complex because we're testing a very stateful thing. We're testing like before the unit tests were fairly straightforward, like, okay, you test every function, the different functionality, but now we have to test a bunch of states. So there's going to be like a bunch of different like conditions we kind of have to think about. So, well, here's an easy one. Test course name returns correct course name. Well, if I create a course where it's CSCI 161, assert equal, I better get back 161. Test the size when it's empty, I get 0. Find on an empty course returns -1. Now, you might wonder, now this is actually a tricky one. I'm testing find here. Often, a lot of people would say you don't test the, often people would say you test the interface to the class and not necessarily everything in there. And because find is a private method, a lot of people might say like, you don't really test that one. You would indirectly test it by virtue of testing the methods that make use of this one. But for our purposes here, I am testing that private method explicitly anyways. Okay, so we test find, so course, I create a course, I create some arbitrary student, and I try to find that student in the course. I never added it to the course, so it shouldn't be there, so I should get back -1. Test remove, empty course raises value error. So I try to remove Bob Smith, I should get back a value error. And by the way, this is how you would check that an exception is thrown with a unit test. With self.assert raise value error, course.remove. If you're wondering, well, what does that mean? It's the magic code for the exceptions being tested. Now you'll notice all the tests so far, yeah, I'm testing each of these methods, but I'm testing them under very specific conditions. They're empty. Or that the class or course is empty. Get a repr on an empty course, I should get back an empty string. Although we saw based on the modifications I made, so this code here is written to test the code that I showed you in the course notes. But you might remember that when I was showing, I modified it slightly. I modified the repr to include the name of the course at the top. So that's why you might be like, wait a minute, why isn't the name of the course there? It's because I added that after in lecture, it wasn't in the code that I gave you. Yeah, test repr empty course returns empty string. And now we go on to like these singleton ones, basically when we have a collection with one thing in it. Because one thing, like when it's empty, that's like a special case. And when there's one thing in it, that's also a special case. So 0 things in it, 1 thing in it, and then many things in it, right? The many things will be like the general case, but 0 and 1 are kind of like special cases, right? They're like at that edge. Let's say the boundary between empty and not empty is 0 and 1. So that's what it's testing there. So test size singleton returns 1. Notice how I didn't test the course name, because the course name, I mean, it really shouldn't matter if it's empty or not. I should get the course name. There's no reason to believe that would have an impact. But size, well, when there's one thing in it, size better give me back 1. All right, so I create a course, Bob Smith, I add that student to it, and I check it's equal. Hopefully by now, too, given that this is a far more complex class than what we've seen so far, this linear collection, see what I mean about all the setup code? Like that one test there required 1, 2, 3 lines of setup code before I could actually do a single call. All right, so there's a lot of setup code there. And each unit test is testing one very specific thing. So if one of these specific things fails, it tells us what's going on. Find on the singleton. Check this out. So I've got find singleton student does not exist returns -1. So I'm looking for, I've got Bob Smith in there, but I'm looking for a student called not Bob. I should still get -1. basically, yeah, it's a non-empty, it's a course with one student in it, but I'm looking for a student that's not there. I should still get back a -1. Yeah. If it had the same student, well, then it would be deemed equal based on the definition there. But you'll notice that they are not the same. It looks like I forgot to actually test contains. My goodness, my unit tests are missing contains. That's brutal. All right, test single and remove. Why am I not testing remove? Oh, no, I do, okay. Oh, I've got contains. Did I check contains on an empty? Find on empty. Remove on empty. Oh, I forgot contains on empty. I know, I better go add that. My goodness. Okay, test find singleton student exists, returns correct index. Okay, cool. Test contains singleton student does not exist, returns false. Does exist, returns true. Remove does not exist, returns a value error. Remove does exist, removes the student. And here's a tricky one, right? This is where, when we have collections that are very interconnected, and they're very stateful, like these methods are very interconnected. Basically, I can't really, I mean, maybe I could have checked contains here. Like if I remove a student, so I add the student Bob Smith and then I immediately remove it. How can I check that it's not there? Well, I would need to use another method that I'm also trying to test at the same time. So it's kind of, we're kind of stuck a little bit here, but this is kind of the nature of the beast. Do you see what I mean where I'm saying like, well, I can't really check remove if I can't use add, and if I can't check if it's there or not, you know? Test repr singleton returns correct string. Test size many students returns correct size. Does not exist, and so on and so on and so on. But do you see how like I started to have to write quite a few tests here, and I missed a bunch even, my goodness. But the point is, these get harder and harder to test, but thank God we have a nice testing framework like unit test to kind of keep track of all that stuff for me. Any questions about what I just showed you there? Cool. All right, let's go back. Excuse me. All right. Searching and complexity. Before we continue, 1 second here. Yeah. Let's really take a moment, like, look, we're near the end of the semester, so let's take a moment and really think about what we've learned this semester. And I'd say you probably have a very difficult time finding another course where you've learned more. And what you can do now versus at the beginning of the semester is like the volume of what you know is crazy at this point. So what have you learned? Well, you know Python and you've got some programming environment you're used to. Most of you have been using Colab. So there we go, you know that. You know how to get like input and output with print and input. You know about types, values, and variables, and literals, right? Remember, literal is the word we use when you just type in the number 5. What's 5? Well, it's the value 5. Why? Because it's literally 5. Versus a variable where like a equals 5. A. Well, what's a? Well, it's 5, but it's the variable 5 as opposed to the literal 5. You've been making use of functions, both in terms of like making use of them, but you've been writing your own functions. You learned about the logic. You learned about like Boolean logic, first order logic. You learned about like Boolean like algebra, how you can like and or things. You learned about comparison operators, which are things that you were familiar with before, but now you're really using them in the context of programming for some very valuable things, very useful. We learned about conditionals. If some condition is true, and those conditions we saw can become quite complex, right? These long Boolean algebraic expressions. We learned about loops, both for and while. That's a great tool. You learned how to use objects. For example, lists. Lists are objects, but lists are very interesting objects in that, like, well, it's a linear collection. It's a very stateful thing, and that's fine. But it's a linear collection of data. It's our first general purpose data structure. We also learned about reference variables and how those are different than, like, not reference variables. Remember that whole thing about, like, aliases? That's a big deal, right? You learned about, yeah, data structures. You know how to read and write data from a file. You learned about exceptions as well. What else? I feel like I'm missing a big one. What did we were talking about lists, data structures, stateful. Oh, you learned about testing, right? You were doing a lot of assert tests. You know how to write your own classes. So not only you know how to use classes in the same way that you know how to use functions, you can call a function. Well, you can write your own classes in the same way that you can write your own function. And right, our classes, they have methods, they have attributes. It's data and functionality kind of merging a little bit. You know how to write your own code. You know how to debug. You know the importance of testing your code. You know how to, like, well, you probably know how to, like, you know enough about Python that when you're stuck on a problem, you could do a little searching online and maybe find some Python documentation or some examples of similar problems that you can make use of to help you solve these problems that you're working on. Like, these are the skills you've developed this semester, and that's a lot to develop. So assuming things are going well, you should feel pretty good about yourself. So the last few topics of this course are heavy on data and data structures. Everything up until now has been really focused on, I mean, not quite true. I mean, the object stuff started to switch to data structures, right? Like the linear collection, the course, it's a data structure. But up until this point, it's been a bit heavy on, like, the algorithms. Now we're shifting to data and data structures. The data structures are built with algorithms, don't get me wrong. But when we think about all those algorithms grouped together, we think of them as a data structure based on their function. Like the list. If you look at under the hood, what is all that? Well, it's a bunch of algorithms, but when you put them together, it makes a list. We have, whether you realize it or not, you've equipped yourself with the majority of the basic tools that a programmer is using all day, every day. Right? An experienced programmer they know a few more tools than you, don't get me wrong. But a lot of their experience just comes with having solved a lot of problems before. That's what makes them so good, is it's getting to the point where, like, they've seen it all. So when they're faced with a new problem, they go like, that problem looks a hell of a lot like this problem I solved 7 years ago, so I know how to do that, right? Like, that's kind of like what happens with the experience. Here, we're going to start to move to focus more on algorithms and how we can use the tools. Yes, okay, so in addition to, like, the data structures, we're going to be talking about algorithms that go with the data structures. And we've been doing this already. For example, searching algorithms. If you have a linear collection, how do you search it? Well, you do a linear search, right? We know that. And we have done this before, but I want to really re-emphasize it. We're going to put a little bit of time into thinking about the amount of work that the algorithm is going to do. And what does it actually mean for an algorithm to be good, or an algorithm to be better than another algorithm? Because these are ideas that we might have an idea of, but what do they really mean? Like, lines of code doesn't mean, like, if you have less lines of code, that doesn't mean your algorithm's better. In fact, that might make your algorithm worse, because it becomes hard to understand if it's just made small for the sake of being small. Like, that doesn't make a good algorithm. A good algorithm is really, we use a couple of different, like, dimensions to describe goodness. One of them is, like, computational complexity, which is, like, how many steps does the computer have to perform to solve the problem? And then there's also space complexity. It's like, well, how much room does your computer require to solve the problem? And then you can talk about things like processor complexity. We're like, well, maybe your algorithm's fast, but it requires 1 billion processors or something, right? All right, a linear search. We should all be experts in linear searches by this stage of the semester. Okay, before I continue, any questions about that little, like, signposting of, like, okay, this is where we are? All right. We should know this algorithm off by heart at this point. It's a linear search. This is like a very basic form of a linear search. Search for a thing. If it's there, return true. If it's not, return false. We've seen variations of this, like return the index. Count the number of occurrences of something. These are all versions of linear searches, but it's the same general idea. Start at the beginning and go over the thing one at a time. So yeah, define linear search, haystack, needle for element in the haystack. If the current element I'm looking at is the thing I'm looking for, I found it. Otherwise, carry on and remember, if I'm doing a linear search, I can conclude that I have found the thing the moment I find it. I can only conclude that the thing is not there after I've looked at everything. I can't look at the top of the pile. Like imagine you came to my office saying, I want to see my test. And I look at the top test on that and I go like, well, is your name like Aaron Andrews? And you go, no. And I'm like, well, you must not be in here. Your test isn't in here. And you obviously know that's a stupid suggestion. Like that obviously doesn't make sense. And yet that's such a common mistake. And it's an easy mistake to make if you're not thinking slowly. Take your time, right? If it's not the first person, maybe it's the next person. Maybe it's the next person. Maybe the next person. As soon as I find you, we're done. I can only conclude that you're not there after I've exhausted looking at everything in the pile. That's the only way I know that the thing I'm looking for isn't there. That's the idea of the linear search. As soon as I find it, return true, but only after the for loop finishes. If I ever completely looked at everything and never found what I was looking for, I'm at the bottom of that list, it's an empty pile, well, you must not be there. Questions, thoughts, concerns, comments, anything? All right. So having a correct algorithm for a problem is obviously important. But we also make sure we have a good algorithm. And a good algorithm, well, what does it mean for an algorithm to be good? I already kind of spoiled this activity. But there are a couple of other things. But yeah, take a moment and think about these things. I'm going to give you a few minutes and talk amongst yourselves these questions. And maybe other questions like, well, what else would make it a good algorithm? How could that algorithm get better? So take a moment and think about these things. Because he's always hiding back there. Oh. And there's, I don't know if there is right there, but there's some right there. It's way too quiet in here for you to be talking about this. Come on. You just think what?
People aren't just excited enough.
They're not excited? Yeah, get more excited. It's like I see some people are talking, but why are you whispering? You don't have to whisper.
I mean, we could yell if you want.
I don't want you to yell. I just don't want you to whisper.
I don't want people to steal our answers.
No.
What if we say something really loud and these people kind What were you saying with space again?
What do you mean?
Well, you like mentioned space.
Well, like, yeah, how much space does the algorithm take? Sometimes your algorithms, maybe one algorithm can run faster, but takes up more like memory than the other. Yeah. Okay, yeah.
Does space really matter for any applications we're really doing right now?
Well, it's funny because the story used to be, back in the day, the story used to be like, well, space is really important, right? We have shitty computers, we have to be worried about space. And then some time went by and we're like, RAM's cheap. Space is cheap, we're in great shape. Computation time, that's the problem. But of course, computation time and space, they're not entirely independent from one another. But then we started to get in the world of like big data. And yes, space matters. Space very, very, very much matters. So there was like that. I mean, who knows what's going to happen next year, right? And it's funny, when it comes to like an engineering perspective, there are ways where you can make a lot of space really cheaply, but it's slow. Like physically it's slow. Like tape, we talked about this. And then you can have like hard disk drives where there's like a motor. Well, that's not too bad, right? That's better. And then you can have something like solid state drives and so on and so on. Now, all right, best case scenario with this linear search, best case scenario, how many things do I have to look at? You give me some configuration of inputs. I'm a linear search. I take 2 arguments. What's the best case scenario? What? It's the first thing I look for. So the scenario is, first of all, let's think about what would the inputs need to look like. Well, I get some long list. Haystack is some long list. But needle happens to be the thing I'm looking at the beginning. You could say, well, what if you get an empty list? Fine, sure. But a lot of times we're thinking about, like, pretend the input size is arbitrarily large. It's size n, where n is some big number, right? But the best case scenario is, in spite of there being n things, the best case scenario is it's only one step. You were Andrew Arthur or whatever the person's name was. Right? You are the first thing I look at. Perfect. Found it. Done. That's the best case scenario. I need to look at one thing. So the total amount of work in the best case scenario is like 1 unit of work. Sure, there's more, right? Okay, set up the loop and everything. But let's keep it simple. Look at the first thing. We're done. Return true. Now, if the question was slightly different of like count the occurrences, well, that's a little different. We're going to have to look at everything. But if I'm happy to just stop as soon as I find something, I'm done. So the best case scenario is the thing I'm looking for is at the beginning, and the total amount of like steps, units of work I need to do is 1. What's the worst case scenario? Should be pretty obvious. Yeah, it's at the end or not even there potentially, right? Close enough, right? So the input is some arbitrary large thing, but the thing I'm looking for is perhaps not even there. And why is it the worst case scenario? Well, I have to put my finger on everything in that list to check. Go all the way down that list until I get to the end and go, it wasn't there. So in the worst case scenario, if the list is size 10, how many things do I need to look at?
10.
If it's size 100, how many things do I have to look at? If it's size 1 billion, how many things do I have to look at? If it's size n, how many things? If it's 10 times n, how many things? 10n. The point I'm making is the total amount of work that algorithm does grows the exact same way that the input size grows. If the list doubles in size, I have to do twice as much work. Okay? Now, on average, how many things am I going to look at? Half of n, because for every time it's at the beginning, it's at the end. It's the second one, it might be over there, right? Like on average, it's going to be like in the middle somewhere, right? So like n over 2. Now, we're really not going to get into this in 161, but maybe we kind of will in the next topic, maybe. But just as a little teaser, whenever we say something is like, well, n over 2, and if something is n over 2, well, clearly that's better than n, because it's like it's half as bad. Computer scientists don't care. We'd say n over 2 and n, it's the same shit. They're linear. Because really, at the end of the day, the question isn't like how much the total amount of work is. It's how does it grow relative to the input size? Think of it. On average, if the input size is n, you had to do n half work, half of n. If I double it, you still doubled the amount of work. I mean, relative to the input size, you could always say, like, but it was half the amount of work. Fine, but the total amount of work that the algorithm did doubled. If I doubled the input, I doubled the total amount of work the algorithm had to perform. If I multiplied it by an order of by 10, I had to do 10 times more work. Sure, it's 10 times n divided by 2, but 10 times n divided by 2 is still 10 times n divided by 2. It's still 10 times the amount of work. So it's still like linear. So that's why we don't really care about the coefficients. It's how much does it grow? How much does the total amount of work grow alongside the input size? That's the big thing we care about. Sure, it's there's some nuance to it, but that's the idea. Any questions about that? All right. How would be what would be the situation to cause a loop only to need to run one? Okay, if it's at the beginning. How much space does your algorithm require? Well, this one's actually kind of easy to answer. It almost might feel like a trick question. How much space? Just however big the input was. I didn't need any additional space, right? The list at size n, well, I needed the amount of space that lets me store that list. So it's linear. But there are algorithms out there that might need to do calculations and save some additional information. Like imagine I said to you, imagine I gave you the problem. I'm going to give you a list of numbers. Okay? So I give you the list 1, 4, 1, 2, 9. Okay? And I say, write the algorithm to give me back. I'm going to make it an easy one, like a cheesy example. Write me an algorithm to tell me what's the difference from one number to every other number in this list. Well, I would have to create like, okay, well, the distance from 1 to 1 is 0, 1 to 4 is 3, 1 to 1 is 0, 1 to 2 is 1, 1 to 9 is 8. And well, that's the distance of 1 to everything else. But now I want to know the distance of 4 to 1. Well, that's -3, 0, -3, -2, 5. Do you see what I'm doing? How far? What's the distance between? What's the difference between 1 and 1, 1 and 4, 1 and 1, 1 and 2, 1 and 9? Then I go, what's the distance between 4 and 1, 4 and 4, 4 and 1, 4, and so on and so on? Well, how big is the thing I'm calculating? If I have a list of length n, so I have n numbers, okay? N numbers. Okay, imagine I've got some list of n numbers, right? I'm not going to like draw them, right? And I want to know what is the difference between every number in that list from every other number in that list? So how many numbers are there? How many other numbers are there in the list from every number? N minus 1, although I was calculating the distance from itself. So really it's n. So I'm going to have like how much room is that? N squared, right? I have n numbers. And for each of these things, I need to calculate the difference between it and numbers. So the total amount, I mean, first of all, how much work is being done here? N squared. And how much space does this take up? N squared. Now you might say, well, it's n, the input size n, plus n squared. But usually when we talk about this stuff in computer science, we don't give a shit about like, we only care about the bad one. And what's a bigger number, n or n squared? N squared is a lot bigger, right? Most of the time. So this is an example of an algorithm that does not grow linearly. Because think about it. If I doubled the input, now look, okay, give me a moment here. If I doubled the input, how much more work do I need to do? 4. 2 squared, right? Think of it, like if I had to do, if this was n, and then suddenly I doubled n to here, you could visualize it, right? Well, I have to like double, and that's like, right? So if I doubled n, I still have to compute like the distance to every other number, and then those extra numbers to every other number, including themselves, and so on. Meaning, this is an example that grows, we call this quadratically. Anyone know why we call, but here's a weird one. I may have said this already. I always remember being like, why are we calling like Square. Quadrat. That's a 2. Why would we call that quadratic? Because it's a square. Squares have 4 sides, right? That's why, if you ever wondered. It took me way too long in life to learn that. So I want you to I'm going to save you from that pain by letting you know now, if you didn't already know that. Be honest, who here didn't realize that? Yeah, you're normal. Blame your teachers from high school or whatever. How did they let you get here without knowing that? I only learned this like 5 years ago, and I was like, oh shit, that makes perfect sense. Anyways. Pardon?
Cubic must have been crazy.
Cubic, yeah, whoa, yeah, cube, why cube? It's a 3 cube, what? Well, yeah. Anyways, so n squared, it grows n squared. If you double the input size, as the input size grows, the total amount of work grows like that. And similarly with the space, right? Because we need to store all that data. Great. Cool. Now you might say, well, in this algorithm, this hypothetical algorithm I'm talking about where I calculate the distance from every point to every other point, or every number to every other number, like if I were to keep going, you would see that sure this is 3 and that's a negative 3, but the absolute difference is the same. You might notice there's really no point to calculate the distance between 1 and 4 and then 4 and 1. I already calculated that difference, right? Doesn't really matter. So you might say, I don't need to calculate the distance from one number to every other number. I only need to calculate, okay, the first number, n0, I calculate from, I don't even really need to calculate its distance from itself, because I know its distance from itself, right? So imagine I've got like a grid, right? I calculate the distance from n0 to n1, n minus 1, all right? I don't really need to calculate this one, but I calculate this one, I calculate this one, I calculate this one, and so on, and I calculate this one, right? But once I get to this number, like, okay, that's n0, n0 to n1, n2, n1, I don't really need to calculate the distance from n1 to 0, because I already calculated it right there. So I don't really even need to calculate that, nor do I need to calculate the distance to myself, right? But then I need to calculate the distance of n1 to n2, to n3, and so on. So far, so good? A lot of people's faces are buried in their computers. There's no way you're understanding what I'm talking about right now. That's a bad choice. n2. Well, there's no need to calculate the distance of n2 to 0, because I already know that. So I don't really even need to do this. Don't need to do this, because I know n2 to n1, that's right there. And I don't need to know n2 from itself, but I need to calculate that and so on. But you might notice I really only needed to calculate, well, let me put it like this. How many calculations are in this first row? n minus 1, right? How many in that second row? n minus 2. How about this row? Right? And so on, all the way down. Where when I was talking about it over here, I was assuming I was doing n to every other thing. So really, each one of these rows was full. So when I was doing the calculation, it was n, and then another n, and then another n, and then another n, and then another n. You add up all these n's together. How many n's are there? N. So n plus n plus n times is, oh my god, that's n squared, right? Well, there you go, cool. But this is different, right? This is different because well, it's less than that, right? Because it's not n plus n plus n. I'm being smart about it, right? I've got a more clever algorithm where clearly I'm doing less work. So n plus 1, well, that's already less than n. Sorry, n minus 1. It's already less than n. N minus 2, that's already less than n. And it's getting even less than n, right? So if I keep going all the way down to the bottom, I'm eventually going to get to like 0. It's going to go down to like 3, 2, 1, 0, right? 0 because, well, I don't need to calculate the distance from the last thing to itself. But how much work is that in total? N squared over 2. Very well, yes, it would be. In this particular example, yes, pretty sure. Now, you may have, like, look, let me put it like this. Let me put it like this. If this is unclear to you, I may have already shown you this, and if I have, you can stop me, because I usually do rant about this several times a year, so you can stop me if I did. But you may notice, hey, 0 plus 1 plus 2 plus 3 plus, for simplicity, let's ignore the 0. And let's just go to n, not n minus 1. Let's just go to n for ease. Does anyone recognize, like, what do we call this? A summation, yes. A series. Can you put those two things together? Summation of a series. Yeah, but we call these like arithmetic series, right? Like, yeah, okay, you just add these things together, right? And who here remembers the special, whenever you see something like this, does anyone remember, like, oh, if you ever want to add up the numbers 1 through whatever, I can calculate the answer like that. You should all know this off by heart, right? You don't? You know why? You have shitty math teachers. Because I'm willing to bet you all learned this at some point, but they never showed you why. So, by the way, if you're like, well, I would have to go through and say 1 plus 2, okay, plus 3. Like, I'm typing this into my calculator, right? And if I have n numbers, how many numbers am I punching into my calculator? N, right? That's a lot of punching. Except the answer, you may discover you could actually figure out the answer like that. And there's a story that goes along with this. Has anyone heard this story before about I think it was Gauss? I could be wrong. Some famous mathematician. He apparently was being a little shit in math class one day. And the teacher just was like, shut up. Go add the numbers 1 to 100 together. Just, busy work. He's a troublemaker. So go add up all these numbers. All right. And he comes back in 2 seconds. He's like, done. And the teacher's like, what? What? How? And he's like, well, obviously, look. Let's, for the sake of argument here, for fun, let's just like double the sequence. Okay? Let's double it. Why not? Exactly. Because here's the thing, at the end of the day, math is subject to our will. We have to operate within its constraints, but we can do whatever the hell we want with it. In the same way we can do programming like that too, right? But we can do whatever we want with math. But we have to be careful. If we ever double something, we could quadruple a number, but when all is said and done, and then do a bunch of calculations, and then when all is said and done, we have to like unquadruple it to get it back to where we want it to be. So we're going to double the series. All right? But, well, what time is it, by the way? 3 minutes. I have 3 minutes? I'm going to do it quickly, I guess. But we got to remember we doubled it. Okay, so we got to remember we got to undo the doubling. So to double it, well, that's just, okay, plus 1, plus 2, plus n. Right? But you may notice, you know what, I'm just going to have some fun. And I'm going to rewrite this second series backwards underneath. Because I like to write like that for fun. 1 plus n plus n minus 1 plus n minus 2. And then you may notice something. Look, it's addition. It doesn't matter. I could add that number plus that number plus that number, which is the same as that number plus that number plus that number, which is the same as that number plus that number plus that. The order doesn't matter, right? But you may notice, what's 1 plus n? Oh my God, it's n plus 1. What's 2 plus n minus 1? Oh my God, n plus 1. Yeah, that little asshole was smart. I don't know, it's an apocryphal story, I'm sure. What's 3 plus n minus 2? Oh my God, it's still n plus 1. Plus, and then what's n plus 1? N plus 1. Great, so we got a bunch of n plus 1s. How many of them do we have? How do you know we have, well, obviously, well, 1, 2, 3, n. So if we have n plus 1 n times, well, look, we don't like to write that out. We say n plus 1 times n. Well, that's the sum of everything, except we doubled it. We doubled the total number, right? So what do we do to undouble something? You just divide it by 2. That's how you can do it. And if you add I mean, we can multiply this out, and then the next thing it's n squared plus n divided by 2. We don't care about coefficients, though. We only care about the big bad ones, and anyways. That's the special formula. I mean, you could generalize it more if you're counting by more than ones. But that's the general formula to add up a series like that. I know, and isn't it crazy how it's just you might look at that math and be like, that's kind of like an algorithm. Yes, that's exactly what it is. In fact, those basic arithmetic operators you've been using since you've been this big are just goddamn operators. Addition, well, that's just simplifying. That's an abstraction of counting. Multiplication, that's just an abstraction of addition. Powers, that's just an abstraction of multiplication. Division, well, that's just the inverse of multiplication. And so on and so on. All right, I'll catch you all later.